Hello, we will now continue with our study of waves by a brief description or a review of transverse and longitudinal waves. I hope you remember what these transverse and longitudinal waves are. When the vibrating particle is at the upper extreme, it is said to be on a crest. And when it is at the lower extreme, it is said to be on a trough. So, a transverse wave is characterized by crests and trough. And we will represent a transverse wave like this. A particle on a crest has gone all the way to the upper extreme. It is now beginning to move down. A particle in a trough has gone all the way down and it is now beginning to move up. Now look at the phase of vibration of a particle on a crest and a particle on a trough. What is the phase difference? When the particle on the crest is beginning to move down, when the particle in a trough is beginning to move up. They are completely out of phase. The phase difference is half a period. And the distance between a crest and a crest is a wavelength. The wavelength is the distance between two adjacent crests or two adjacent troughs. Alright, so that is a wavelength. How about a longitudinal wave? A longitudinal wave is characterized by compressions. Now remember, in the case of a longitudinal wave, the particles move back and forth like this, and the wave advances either to the right or to the left or in both directions. Now, a longitudinal wave is characterized by compressions, a region where the particles are closer together, and rarefactions where the particles are farther apart. Now here you can see the vibration of this string back and forth sets the particles of the medium in back and forth vibration. And you can see that causes in some regions particles to be closer together. There you got compression, and regions where particles are farther apart called rarefactions. These compressions and rarefactions are advancing in the medium, and that is an example of a longitudinal wave. The wavelength is the distance between two adjacent compressions or two adjacent rarefactions. Alright, now it is time for us to go and start talking about sound waves. Now tell me, how is sound produced? Now you hear a sound produced. Well, another sound, another sound. Sound is actually produced by setting objects into vibration, right? So sound is a form of energy and the energy needs a material medium to propagate through. Now, when I speak, if there is no air between me and the camera, you will not be able to hear my speech. In fact, sound can only travel through a material medium. And sound is propagated through solids, liquids, and gases. Now, in the form of longitudinal waves. So, sound is a form of longitudinal waves. When I speak, my voice cord set particles of air into vibration. What kind of vibration? Back and forth vibration. And the vibrations of the particles create compressions and rarefactions in the air as the particles move back and forth. Now, pay attention to this. When the particle moves in the direction of the wave, all the particles are together, you got a compression. When the particles, now when it vibrates, you see it moves to the right and then to the left. As it moves to the right in the direction of the wave, it is in a region of compression. When it moves to the left, the particles are farther apart. It is in a region of rarefaction. So in a longitudinal wave, the direction of particle vibration is the same as the direction of propagation of the wave. For example, if the wave is propagating to the right, the particle vibrates right and left. You see, there's a big difference between transverse wave and longitudinal waves. So the particle vibrates like this, the wave goes to the right and left. Now, sound is produced by vibrating objects. Now, I'm going to set an object into vibration. Now, here you can see an object I can set into vibration, and listen to this sound. Isn't that a beautiful sound? So sound is produced by vibrating objects. My voice cord is vibrating, producing the sound you hear. Now, when you set a tuning fork or a metal strip, what you heard is the vibrations of each of these prongs. Now, a vibration is a back and forth vibration. So you can see a vibrating object, the center position is called the equilibrium position, you know that. And the object vibrates between a left extreme and a right extreme. A vibrating object has an equilibrium position. Equilibrium position is the center position, and two extreme positions, the left extreme and the right extreme. As the vibrating object moves from one extreme to the left, from the extreme left to the extreme right, particles of the medium are pushed to the right. And that means as the vibrating object moves from left to right, the particles are all pushed to the right. They form a region of compression. You see this one? Particles are all pushed together. They are in a region of compression. And when the vibrating object moves back from right to left, the particles are pulled back into that space. And that is a region of rarefaction. So what is a region of compression? A region of compression is a region where particles are closer together. Now, this region of high density, this is the compression, is a region of high density, and that gets propagated. A compression gets propagated in the medium. Now, as the vibrating object moves from right to left, particles of the medium are pulled back, and that creates a region of rarefaction. So, you must understand, if a particle is in a region of compression, the direction of motion of that particle is the same as the direction of the wave. If a particle is in a region of rarefaction, the direction of motion is exactly opposite. Now let me see if I can draw that for you. If a particle is in a region of compression, now look at this particle. The direction of vibration of that particle is to the right. On the other hand, if the particle is in a region of rarefaction, it moves to the left. So, when a particle moves to the right, it is in a region of compression. When a particle moves to the left, it is in a region of rarefaction. So, as this particle keeps vibrating, to the right, left, right, left, right, left. It gets into regions of compression, regions of rarefaction, regions of compression, regions of rarefaction, and these regions of compressions and rarefactions are propagated through the medium until it reaches your eardrum, and that sets your eardrum into the same vibration, making you hear sound. Okay, let's move on. Now, when the particles vibrate in the direction of the wave, they are in a region of compression, and when the particles vibrate opposite, they are in a region of rarefaction. The compressions and rarefactions in a longitudinal wave is analogous to the crest and trough of a transverse wave. For a transverse wave, the particle positions are characterized by crest and trough. On a crest, the particle has reached the maximum, it is beginning to move down. On a trough, the particle is beginning to move up. Is that right? So the particles are exactly opposite phase. In the same way, on a compression, the particle is moving to the right. The rarefaction, the particle is moving to the left. They are in opposite phase. So the compression and rarefaction in a longitudinal wave is similar to the crest and trough of a longitudinal wave. So when you want to draw a longitudinal wave, we can draw it by using a transverse wave. Now, we will do that from now on because it is easy to draw a transverse wave. It's much difficult to draw a longitudinal wave. It is difficult to draw the compressions and rarefactions. So from now on, in order to draw a sound wave, I will use a transverse wave representation. Look at this. But when I draw a transverse wave, a crest will represent a compression, a trough will represent a rarefaction. I hope that is clear. When I draw a transverse wave like this to represent a longitudinal wave, a crest will represent a compression and a trough will represent a rarefaction. Okay? So the vibrations of particles at the center of a compression differ in phase by particle at the center of a rarefaction by half a period, And the wavelength of a longitudinal wave, you know, is the distance between two adjacent crests. Now, from the center of this crest to the center of the next crest is a wavelength. All right. Now, let me see if I can show you a longitudinal wave in setting a particle into vibration. What you see here are the vibrations of a tuning fork, and you can see as the tuning fork vibrates to the right, it creates a compression. It goes to the left, it creates a rarefaction. And compressions and rarefactions are created continuously as the object vibrates back and forth. And these compressions and rarefactions advance to the right. Is that right? Okay. Let's now talk about the speed of sound waves. How fast does sound wave travel in a medium? Now, the speed of sound waves in a medium depends on how fast the particle vibrations are transmitted in the medium, how fast the particle vibrations are communicated from particle to particle. In other words, it actually depends on how well the particles are held together. Is that right? Now, it largely depends on the elastic properties and the density of the medium. So tell me, where do you think the sound will travel faster? In a gas or in a solid? Well, as I told you, the speed of sound in a medium depends on how well the particles are connected together. You see, in a gas, the particles are not connected together well, because in a gas, the particles are sort of separated. That means, in order that the vibration of one particle may be handed over to another particle, it takes some time. Whereas in a solid, the particles are connected together. The vibration of one particle can be communicated to the next particle very fast. That means sound travels very fast through solids. You see, in the olden days, somebody waiting for a train in a railway station used to go and put his ear on the track, on the train track. You know why? He can hear the train coming from a distance of about 100 miles through the rail track. It takes a very long time for sound to travel through air, but through steel it travels very fast. So sound travels much faster in solids and liquids than in air. The speed of sound in air at room temperature is about 340 meters per second. So sound travels in air 340 meters in 1 second. And in steel, it travels almost 5 kilometers in 1 second. So it travels very fast in solids. The speed of sound in water at 25 degrees is 1,500 meters per second. You see, sound travels in air at 340 meters per second. In water, it travels at around 1,500 meters per second. And in steel, it's about 6,000 meters per second. So you can see a comparative study of the speed of sound in air, in water, and in steel. As I told you, the speed of sound in air depends on the pressure P. You see, air is characterized by its pressure and density. And you have, now because of these values depend on the temperature, the speed of sound in air varies with temperature. Now, although I wrote here, I'm going to give you an equation, I don't think you need to worry about an equation for the speed of sound. But you need to understand this. The speed of sound in air depends on temperature. Why? Because as temperature changes, the density and pressure of air will change. Now, there is a very simple relation connecting the speed of sound and the temperature. An approximate relation connecting V0. V0 stands for speed of sound in air at 0 degrees Celsius. And V sub T stands for the speed of sound in air at a temperature of T degrees Celsius. Now look at this relation. V sub T equal to V0 plus 0.6 T. In other words, if you know the speed of sound at 0 degrees Celsius, add to that 0.6 times the temperature, you will get the speed of sound at a particular temperature. Alright, we will use this to do small calculations. Alright, the speed of sound at 0 degrees Celsius is 331 meters per second. That is, this is V sub 0. Find the speed of sound in air at 30 degrees Celsius. Alright, bring back our equation. We have V sub T equal to V sub 0 plus 0.6 T. Now, V sub 0 is the speed of sound at 0 degrees Celsius, and that is 331 meters per second. And what is the value of T, the temperature? 30 degrees Celsius. So using that value, we get V30, means speed of sound at 30 degrees is 331 plus 0.6 times 30, that is 349 meters per second. Alright, now I'm going to do a couple more problems which will help you to get back that wave equation. Do you remember the wave equation we defined some time ago in the last lesson? The wave equation is V equal to F lambda. You must remember that equation. That is the wave equation. Wave speed depends on frequency and wavelength. Wave speed equal to frequency multiplied by wavelength. Okay, once you know that, we can do a number of problems using that. Alright, let's read this problem. The annoying sound from a mosquito is produced when it beats its wings at an average rate of 600 beats per second. Mosquito beats its wings at 600 beats per second. What does that mean? It means the frequency of vibration is 600. Alright, what is the frequency in hertz of the sound wave? The frequency is the number of vibrations per second. Alright, assuming that the sound moves with the velocity of 340 meters per second, what is the wavelength of the wave? Alright, the frequency is the same as the number of wing beats per second. So what is the frequency there? Frequency is 600 hertz. And in the next part, we know the frequency is 600 hertz. We know the speed is given at 340 meters per second. Can you calculate the wave speed? What is the wave equation? The wave equation is V equal to F lambda. We know V, we know F, we need to find lambda. So what do? Divide both sides by F. If you divide both sides by F, we get lambda equal to V divided by F. Is that right? Let me show that to you quickly. Now, divide the left-hand side by F, the right-hand side by F, and you notice F and F will cancel. We get lambda equal to V over F. You see, when you divide both sides by F, F and F will go. Lambda equal to V over F. That's what I wrote there. So we can now find lambda. We know V equal to 340, F equal to 600. Therefore, lambda equal to 340 divided by 600. That is 0.57 meter is the wavelength of the wave created by the wing beatings of the mosquito. Okay, let's do another one. An elephant produces a 10 Hertz infrasonic grunt. What is that infrasonic? You see, sonic is something that you can hear. Infrasonics are frequencies that you cannot hear. Low frequencies. You see, if you make the frequency very low, can you distinguish between high frequency and low frequency? Low frequency. Oh, high frequency. You see, there are limits to our audibility of frequencies. Beyond a certain limit, if the frequency is too low, you cannot hear it. They're called infrasonics. And if the frequency is too high, again, we cannot hear it. They will be called ultrasonics. All right, so the elephant grunt is 10 hertz. You see, I can beat this 10 times a second. Can you hear the sound? No, I can't hear. It's infrasonic. Well, the frequency is 10 hertz and the speed is again given to us. Well, same problem. Frequency is given, speed is given. Find the wavelength. You know, wavelength is speed divided by the frequency. That is 345 divided by 10. That is 34.5 meter. You see, when the frequency is small, the wavelength is very big. I want you to appreciate that concept. As the frequency gets higher and higher, the wavelength becomes smaller and smaller. Alright, let's now talk about reflection of sound. How does sound get reflected? When I speak in this room, actually the sound gets reflected from the walls. And what you actually hear is a superposition of the sound I produced and the sound that gets reflected from the walls. Now, when a sound wave reaches the boundary between one medium and the other, a portion of the wave undergoes reflection and another portion goes into the medium or it gets transmitted. Now, reflection of sound waves off surfaces can actually lead to two phenomena, and these are echo and reverberation. What is an echo? Have you ever heard the echo of your own voice? If you go on a very hilly area and stand on a hill and say hello, you can keep hearing hello, hello, hello. It will keep repeating. That means your sound gets reflected from other hills, thrown back at you. And that is echo. And when the echoes keep repeating, you have reverberations. Reverberations are repeated echoes. If a reflected sound wave reaches the ear within 0.1 seconds of the initial sound, it seems that the sound is prolonged. You see, when I speak, if the reflected sound from the wall reaches me within 0.1 second of my speech, then my speech sounds as though it is prolonged. Alright? Now, the reception of multiple reflections of walls and ceilings within 0.1 seconds of each other cause reverberations or prolonging of a sound. I don't know whether you have heard about the Taj Mahal in India. It is a big dome. It's actually a monument created by a king for his wife. This is a big dome. If you go there and stand inside and speak, you can hear, suppose you say, my name is George. It will keep on saying, my name is George, my name is George. You see, you keep hearing that prolonged reflections. That is reverberations. It's a beautiful experience. Now, there is another concept called the whispering gallery. It's a very round kind of a structure. Now, the story goes like this, that two lovers were standing at one corner and whispering to each other their very secret stories. And somebody standing 5 meters away from them could hear them very distinctly. You know how? Because the sound from them got reflected several times off the wall, taking the sound close to the other person who was trying to eavesdrop. So be careful. when you are in places like that, somebody can hear you when you whisper. Now, smooth walls in an auditorium causes too much reflection, which does not produce a pleasing effect. You see, in some rooms, if you go, sound will drown. Well, if you speak there, your sound will get drowned by the reflection. In other words, you will not be very pleasant. The sound produced in that room will not be very pleasant to listen to. I'm sure you have experienced those kind of situations. Now, sound will get reflected from all over. So smooth walls fail to give the room a feel of full sound. Smooth walls are good reflectors. So reflection of the sound will drown the original sound, so you will not really appreciate, you will not be able to hear or distinguish what the speaker is actually saying. Whereas rough wall gives the room a full and lively sound. Rough walls are not good reflectors. So a good auditorium or a good classroom will have rough walls and window shades that are very bad reflectors of sound. Now, rough walls give full and lively sound. Now, the science of constructing an auditorium for maximum pleasing effect. You see, in an auditorium, echo is good, and echo can enrich one's sound. Now, how many of you sing in the bathroom? I think most people like singing in the bathroom because the bathroom produces a pleasing effect by enriching your sound by the echoes. Now, when you construct an auditorium or a theater where people come to listen to the speaker, now the sound needs to be pleasing. It has to be distributed uniformly in the room. And the science of constructing such auditoriums is actually called acoustics. And a well-constructed, acoustically constructed auditorium will use rough walls. Next time you go into a theater, have a look. The walls will be rough, and the windows and doors will have very poor reflectors as the shade. Alright, so all these acoustical properties are very important for the transmission of sound. Let's now talk about diffraction and refraction of sound. All these are characteristics of waves. So, first we talked about reflection. Waves can be reflected. Now, we're going to now talk about two other properties of sound waves. What is it? Diffraction. What is diffraction? When I speak in this room, somebody else can hear me in the other room. That means sound can travel out of this room and bend and go into the other room. You see, unlike light, light can only travel in a straight line, but sound can go around corners, and that property is called diffraction. Diffraction involves a change in the direction of wave as they pass through an opening or around a barrier in their path. You can see this is where I'm standing and speaking, and the sound waves are advancing forward. When they come to the door, they can actually bend, you see, and this is the property of diffraction. So diffraction of sound waves is commonly observed. We notice sound diffracting around corners or through door openings, allowing us to hear other people who are speaking in adjacent rooms. Well, do you like it? Well, sometimes it is very annoying. Is that right? What is refraction? Refraction occurs when sound travels from one medium into another. Now what does that mean? So refraction of waves involves a change in the direction of waves as they pass from one medium into another. Now look at the way refraction occurs. As sound waves come in, is traveling from one medium into another, the direction changes. The direction suddenly changes. Now, if you go on a bicycle on a properly tarred road, and all of a sudden you come to a sandy road, what will happen to your speed? Your speed will suddenly decrease, and as a result, you will be deviated, you will be thrown away. Now, this direction, the change in direction of the sound waves as it enters from one medium into another is due to the sudden change in the speed. And that is what is called a refraction. So, refraction or bending, you can see waves bend, of the path of waves is accompanied by a change in speed. If sound waves travel from air into water, its speed will suddenly change, and that sudden change in the speed will cause a bend in this path, and that is what we call refraction. Now, very often you know that warm air is less denser than cold air. So if you stand on a lakeside and speak, you see the air around you here is probably colder, well, or warmer than the air above water. That means as sound travels along this medium, it is traveling from a denser air to a less denser air. It is like traveling from one medium into another. As a result, the direction of sound waves will change. Look at that. So if you speak from here, the sound will reach this point rather than it traveling directly. And this effect is due to the refraction of sound. So refraction of sound waves is most evident in situations in which sound wave passes through a medium with gradually varying density, like this, a gradually varying density, which results in the direction of the wave gradually changing. Well, we are now going to look at a very interesting phenomenon of sound waves, interference. Now, I want you to understand this concept. What does interference actually mean? Now, when one sound meets another sound. Now, you must understand a sound is produced by setting particles in a medium into vibration. So what does it mean when two sounds reach a point at the same time? It means the same set of particles are subjected to two different disturbances. This particle will be disturbed by sound 1, also disturbed by sound 2. So this particle will have to now vibrate according to the instruction coming from sound 1 and sound 2, and how will it then behave? Let's talk about that. That is interference of sound. Now, sound is a pressure wave, is that right? Sound is a pressure wave. What does that mean? As the particle vibrates, it creates high pressure and low pressure regions. In other words, we call them compressions and rarefactions. Now, do you recall the directions of motion of particles? The direction of motion of a particle. If this particle is in a region of compression and it moves to the right, Now, a particle in a region of rarefaction will be moving in the opposite direction. Now the question is, try and answer this question. Suppose two sound waves reach this point. According to the first sound wave, this particle is in a compression. And according to the second sound wave, this particle is going to be in a region of rarefaction. That means the first sound comes and makes it move to the right. The second one wants this to move to the left. So what will this do? If the compression of one wave falls on the rarefaction of another wave, this particle is forced to vibrate to the left and right at the same time. The particle will not vibrate. They will cancel each other. That means when a compression of one wave meets with the rarefaction of another wave, what will happen? Those two will cancel each other. There will be no wave. It's a very important and interesting phenomenon. So as a compression passes through a section of a medium. Now, if this is one particle of a medium, and if a compression passes through this medium, the particle now goes to the right. You see? So if a compression passes through a section of the medium, it tends to pull the particles together into a small space, creating a high pressure region. A rarefaction tends to push particles apart. So in a compression, the particles are pulled together. In a rarefaction, the particles are pulled apart. Now, if a compression of one wave meets up with the compression of a second wave, tell me what will be the result of that? If a compression of one wave, suppose I am speaking from here, that is wave 1. Somebody else is speaking from another place, wave 2. Now, wave 1 and wave 2 arrive at this particle. And wave 1 produces a compression here. Wave 2 also produces a compression here. What does that mean? It means, according to wave 1, this particle is moving that way. And according to wave 2 also, it has to move that way. That means it will now move double the distance. So, if the compression of wave 1 and the compression of wave 2 falls at the same place, they two will add up, producing a bigger compression. There you are. So if a compression, I told you, a compression will be represented by a crest. Alright? You understand that? So I'm using a crest to represent a compression. I have a blue wave and a red wave. So there are two waves meeting in one place. The compression of the blue wave and the compression of the red wave are both meeting at the same point. What will happen? You get a bigger compression. So a compression of one wave meeting with the compression of another wave produces a bigger wave. You see that? According to one wave, this particle moves that way. According to the second wave, it moves in the same direction. Therefore, it will move double the distance. You see? So, a compression of one wave falling on the compression of a second wave produces a bigger compression. Similarly, the rarefaction, I'm representing a rarefaction by a trough. A rarefaction of one wave falling on the rarefaction of a second wave produces a bigger rarefaction. As a result, you have a bigger wave, or you hear a big sound. You see? So when two waves meet at one point, with compression of one wave falling on the compression of the other wave, they interfere constructively. It's called constructive interference. It means they reinforce each other. They produce a loud sound. Now, have you ever experienced that? If two sounds meet at a point in phase, you understand the meaning of in phase. In other words, if one wave makes this particle move to the left, the other also will make it move to the left. They are in phase. That will produce a bigger wave. That will produce a bigger sound. So, this is called constructive interference. The compressions and rarefactions reinforce each other, producing a loud sound. On the other hand, if the compression of one wave meets with the rarefaction of the second wave, what will happen? If two sound waves interfere at a given location in such a way that the compression of one wave meets up with the rarefaction of the second wave, that means the first wave tells this particle to move right. The second particle makes that particle move to the right. So if one makes it move to the right and the other makes it move to the left, what will this do? It will stay where it is. You see, if my right hand wants to move this to the right and my left hand wants to move this to the left, tell me, look, my right hand is trying to pull it this way. My left hand is trying to pull it to the left. Where is it going? It's not going anywhere. That means if the compression of one wave falls on the rarefaction of another wave, then particles in a medium at that point are subjected to displacements in the opposite directions. They will cancel each other. They will destroy each other. Or we call such an interference a destructive interference. So what is a destructive interference? The compression of one wave falls on the rarefaction of the other wave. You see, the compression of the wave will make the particle move to the right. The rarefaction will make it move to the left. So, suppose this is the particle. I'm going to make that big particle there. Now, according to the first wave, that particle is asked to move to the right. And according to the second particle, this particle is asked to move to the left. You see that? Wave 1, the compression of one wave makes this particle move to the right. The rarefaction of the second wave makes the same particle move to the left. What will happen? The particle will not move. They cancel each other. In other words, such an interference is called a destructive interference. The tendency of the compression is to push the particles together, and the tendency of a rarefaction is to pull them apart. That means if the compression and the rarefactions fall at the same place, their effect will be cancelled. The crest and trough of a transverse wave is similar to the compressions and rarefactions of a longitudinal wave. And that's the reason why I used a transverse wave representation to draw the compressions and rarefactions. So, when a compression falls on a compression falls on a compression, you hear a loud sound. And when a compression falls on a rarefaction, you hear no sound. Now, here's an illustration. One sound coming from the left and the sound coming from the right, they interfere. And watch where the compressions become darker. When compression falls on compression, you get darker regions. Loud sound, no sound, and so on. So as these two sound advance, if you stand at one place, you can hear loud sound, no sound, and so on. But in practice it is very difficult, because the sound you hear is not only the direct sound but also the reflected sound. So in practice you may not be able to actually detect this. Now here is a good example. Now there are two loudspeakers, S1 and S2 are two speakers. I'm sure most of you have speakers in your living room, one on the left side, one on the right side, and you are hearing sound from both speakers. Now if you are standing here, over here, sound coming from loudspeaker 1 and loudspeaker 2, if they arrive in phase, what is the meaning if the sound arrive in phase? The compression of one falls on the compression of the other. That's what means they're in phase. Then you hear a loud sound. Whereas if the sound coming from the two speakers are out of phase, what does that mean? It means the compression due to one wave will fall on the rarefaction of the other. Then you hear no sound. So actually if you walk from left to right, this is something that you can actually do. If you walk from left to right, there will be points where you hear loud sound, and there will be points where you hear no sound. You can see how they interfere. They interfere constructively. Those darker regions you see are where they interfere constructively. You can hear loud sound. And the lighter shading is where they interfere destructively, no sound. So since this is, the animation is very fast, you see loud sound and no sound here, loud sound along the shaded region. So you can actually hear, I did this experiment when I was in school. My teacher arranged it, and the room needs to be all prepared because the reflections needs to be minimized. If there are too much reflections, then they will interfere and we will not be able to experience this. All right, let's move on. As you walk from left to right, you can actually experience loud sound, no sound, loud sound, no sound, and so on. So this is the wave from speaker 1, look at that. And this is the wave from speaker 2. And tell me, are they in phase or out of phase? Look at this. The compression falls on compression, rarefaction falls on rarefaction. You got a much bigger wave, you hear a loud sound. Alright? Whereas, if this is the situation, watch this one. The compression of one wave is on the rarefaction of the second wave. I hope you understand when I'm keeping this tick. The compression of one wave is on the rarefaction of the other. They are completely out of phase. That means the sound from speaker 1 and speaker 2 will destroy each other and you get no sound. So this is where you get loud sound and this is where you get no sound. That's the beautiful effect of sound. Alright? You can try and reproduce it at home if you have some time. Now here is another example. Two sound waves advancing. You see how it behaves. There are two particles here. When the two waves are in phase, look at that. Now this is maximum displacement. Now gradually they get out of phase, no sound. You can see as these two sound waves advance, the particles, the waves will be in phase, out of phase, in phase, continuously producing, watch this, there is no wave now, the bigger wave now, and now no wave, a big wave. These two waves can get in phase and out of phase, producing loud sound followed by no sound, loud sound followed by no sound. This is a beautiful experience in sound. I'll try and show you some of that as we go on. So, let's now discuss this interesting feature called beats. Beats. What are beats? When two sounds of nearly the same frequency are sounded together. If you can sound two sound waves together of very nearly equal frequency, then what will happen? As the two waves advance, they get in phase and out of phase alternatively, just like I showed you. Now, this is wave 1. Now, watch how they differ. The wavelength of the wave on the top is slightly bigger than the wavelength of the wave at the bottom. So, as they advance, if you watch carefully, now watch my stick that I'm holding there. Can you see that? These waves are here, they are in phase. But gradually as they go, look at this, they have now become completely out of phase. If you come here, the compression, can you see where I'm pointing? The compression falls on the rarefaction. They have completely gone out of phase. So here they are in phase, here they are out of phase. They are in phase, I can hear a big sound. You see? So this is constructive interference, this is destructive interference, this is constructive interference. As these two waves advance, what you will hear is they will get in phase, out of phase, in phase, out of phase continuously. Look at this. They are in phase, the crest, the compression falls on compression. You get a big wave. A compression falls on rarefaction. Watch this. A compression falls on rarefaction. You get no wave. Now, a compression falls on a compression. You get a big wave. And this process is repeated, and you will hear a loud sound, no sound, loud sound, no sound. I will try and see if I can produce this for you. Now, this phenomenon is called beats. Now, the question is, how many times will they get in phase and out of phase? Now here, the first frequency is 40 Hertz. The second wave, the frequency is 50 Hertz. That means they will get in phase and out of phase 10 times a second. You will hear 10 loud sound and 10 no sound. So you will hear loud sound, no sound, loud sound, no sound 10 times in 1 second. The number of beats heard per second is called the beat frequency. And the beat frequency equal to the difference between the two frequencies. So the difference between the frequencies of these two is the beat frequency. Alright, now watch this animation here. This is the animation of the same thing I was talking about. Now, the wave at the top and the wave at the bottom differ by a small frequency. Now look at this, they are in phase, there, big sound wave. And now they are soon going to be out of phase. Now, I'm not going to move away from here. I'm going to stand here. Can you watch what I'm pointing? Alright, a particle here. Alright, I'm going to move here. Watch that particle. and look at the way that particle behaves. This particle now has maximum displacement there, loud sound. And now this particle has no displacement, no sound. So, as these two waves advance, they get in, over here, they get in phase, now they are in phase, and soon they are going to be out of phase. That's right, they're out of phase. And now they're going to be in phase, there you are. And now they will be out of phase. That means you keep hearing loud sound, no sound, loud sound, so on. And this phenomenon is called beats. I promised you that I will demonstrate the effect of beats. Now, what is the phenomenon of beats? If two sounds are produced which are of slightly different frequencies. Now, I can produce a sound here which has a frequency of 288 Hertz. Now, listen to this sound. Alright, I'm going to produce another sound which is of slightly different frequency, which is 280 Hertz. Listen to this. Well, let's see. Can you distinguish the difference in the frequency? I'm going to sound them one more time, one at a time. This is the first frequency. Listen to that. Okay. And the second one. Well, I'm not holding it rightly, so watch this again. Okay, now what I'm going to do is I'm going to sound these two together. That means you will be hearing when these two sounds reach the camera at the same time. What will happen? The place where the camera diaphragm is, the microphone is, these two waves will arrive in phase, out of phase, in phase, out of phase, continuously 6 times a second, because yes, 6 times or 8 times. One is 388, the other is 380. Is that right? Alright, now listen to this. I'm going to set one into oscillation. Since I can only hold one, I'm going to set one into oscillation and keep it down. Now, can you hear the beats? Listen to this again. I'm going to set the first one vibrating. Now, I've got to handle both these at the same time. So try and listen to this carefully. I'm going to set the first one into vibration. Can you hear that? The sound goes... Try it one more time. Okay. Let's see how best I can do this now without... listen to this again. Oops. Did you hear that? That's so very clear. Well, I'm going to produce one more time, and then I'm going to change the frequency. All right, listen to this one more time. Two frequencies together. Now, I can actually change the frequency of this slightly by moving this down. And let's see if there is any difference now. You didn't hear any difference? Well, let's see. Hear it one more time. Yes, the beat frequency has increased. Is that right? Okay, Let me see one more. Now it didn't work very well. One more. It's increasing at a much slower rate. That means the frequency is now very close to each other. So this is the phenomenon of beats. Okay, I hope you got a fair understanding of that concept. Let's now talk about intensity and loudness of the sound. Now, what does the loudness depend on? Now, there are people who say loudness depends on the frequency. No, frequency has nothing to do with loudness. Now, for example, no matter how hard I hit this, the frequency of vibration will not change. Try and listen to this sound. I'm going to hit very low energy. Well, okay, now I'm going to hit it hard. You can see that both sounds are of the same frequency, but one is louder than the other. So tell me, what is it that makes a sound louder? Now, a sound becomes louder when the amplitude of vibration is bigger. What is the meaning of amplitude? Now look at this particle vibrating. Alright? This is very small amplitude. Now, this is large amplitude. If you can hit an object so that it vibrates with large amplitude like this. Now, that's a loud sound. Whereas if I hit it so that its amplitude is small, that is not loud. So loudness of a sound is determined by the amplitude of vibration. The amount of energy which is transported. When I keep an object vibrating, when an object produces sound, now it is sending out energy in all directions. That means a certain amount of energy actually crossed my ear. That's the reason why I hear it. So, the amount of energy which is transported past a given area of a medium per unit time is known as the intensity of the sound wave, and the loudness is determined by its intensity. You see, when the amplitude is very large, there is large amount of energy sent out. That means the amount of energy I hear, the amount of energy I receive will be large. My eardrum will vibrate with larger amplitude. Is that right? I know most of you in your car has your speaker sort of geared up so that the road will vibrate. I have experienced that. When you park next to a teenager's car, you feel that vibration. But remember, your eardrums are continuously being subjected to that abuse. I say that abuse because that is really an abuse. Your eardrum is being abused. So be careful how much stress you subject your eardrum to. Now, I read a statistics recently that a lot of people in their 30s and 40s are now seeing the doctor with hearing problem. And that problem is a lot of people wear Walkman, you know, these microphones that shove into your ears, and also these big sound, especially in the confined interior of a car, that can be very damaging. So take care of your hearing and your eardrums. Don't subject your eardrums to too much of pressure. Okay, now therefore, what is loudness? What is intensity of a sound? The amount of energy which is transported past a given area of a medium per unit time is called intensity, and loudness is determined by intensity. A greater amplitude of vibration makes the wave more intense and therefore of loud sound. Now this particle, what's the amplitude of that particle? Small amplitude corresponds to low energy. A large amplitude of vibration corresponds to a bigger amount of energy. So intensity of the sound wave decreases with increasing distance. You see, the amount of energy, if I set this tuning fork into vibration, the amount of energy crossing my ear will decrease if I move away. As the distance from the source increases, the amount of energy reaching me will also decrease. As the distance increases, the energy will decrease. Now, here is the loudspeaker, and as you move away from A to B to C, the amount of energy that reaches you will be decreasing. That means the loudness or the intensity will be decreasing as you move away. Now, intensity at a point is a measure of the power crossing unit area placed at that point. In other words, if you place a unit area, now what is a unit area? A unit area is an area that is 1 square meter. Suppose this is a unit area of 1 meter multiplied by 1 meter. How much is the energy crossing that unit area? If I place that unit area here and measure the amount of energy crossing that unit area, that will be a measure of the intensity. So intensity at a point is a measure of the power crossing unit area placed at that point. So if I place the unit area at A and then move it to B and then move it to C, which of those places will be more power crossing that unit area? More power will cross that unit area when it is placed at A. As we go away from the speaker, the power crossing that area will become less and less. And look at the unit for measuring intensity. It is measured in a unit called watt per meter squared. Now, do you remember the unit watt? Watt is joules per second. That is the unit of power. The energy passing per second is watt. And that how many watts are passing the unit area, and that is a measure of the intensity. Now, the faintest sound which the human ear can detect is known as the threshold of hearing. What is the faintest sound? Now, try and concentrate and breathe. Can you hear the sound of your breathing? Well, barely. A sound that you can barely hear is called the threshold of hearing. You cannot hear sound of intensity less than that. So the threshold of hearing is the minimum intensity that is audible to our ear. The range of intensities which the human ear can detect is very large, and physicists use a scale based on multiples of 10 to measure that range of intensities. Look at this. The threshold of intensity is 10 to the power of negative 12 watt per square meter. Now, we have seen this number before. 10 to the power of negative 12. It is 1/trillionth of a watt per square meter. 1/trillionth. 1 part in a trillion. So that is the threshold of intensity. In other words, the minimum intensity our eardrum can pick up is 1/trillionth of a watt per square meter, the threshold of intensity. And we can actually hear a wide range of intensities. Now the scale based on this is called the decibel scale. So the loudness that you hear is actually measured in a unit called decibel. So let's see what it is. If you now look at some of the familiar sounds, threshold of hearing is 10 to the power of negative 12 watt per square meter. And I said you're breathing. Well, not this. If you breathe like that, that is much more than the threshold of hearing. But when you meditate, I don't know how many of you can meditate, you can hardly hear your own breathing. That is the threshold. That is 0 decibel. You see? 10 to the power of 0. No, that is 1. Is that right? So, rustling of leaves. If you hear wind comes and the leaves rustle in a tree, that is 10 to the power of negative 11. 10 decibels. Alright? What is the decibel level of whispering? If I tell you, well, don't tell this to anybody. Now, did you hear me saying that? Well, whispering is about 20 decibels. The normal conversation is about 60 decibels. Well, when I lecture here, it is much more than a normal conversation. You see, when you listen to my lectures, always make sure you keep the volume down. Otherwise, I'll be shouting into your ears, because I have a normal tendency to speak very loud. So my speaking is almost between 70 and 80 decibels. A vacuum cleaner, you know, it doesn't produce very pleasing sound. That's about 80 decibels. A large orchestra is 98 decibels. And if you go to one of those parties where you got these boom boxes, big speakers, and if you sit close to one of those speakers, you are sure to get that earache, because your eardrum will be beating hard and fast. Well, threshold of pain, that is what you will have if you sit near that big speaker. That is 130 decibels. And I'm sure most of the speakers in the teenager car that I was talking about, not all, don't misunderstand me, I'm talking about few people, not all. Well, it could be as close to 130 decibels. But why I did say that, because all these are important aspects. You don't want to pollute the atmosphere with that big sound, because the other people will not be very pleased about what you do in your car. Not only that, it is not good for you. So please take care of yourself. It's very important. Well, what I'm going to do is I'm going to record a third part of this lesson as we go on. So since I'm spending a lot of time showing you the demonstrations, I spend a lot of time on all these things. So watch these tapes very carefully and learn these concepts. And I'm going to go to the next concept in the third part of this lesson.